Welcome. You know that feeling when you look at a fraction that's just jam-packed with x's and squares, and your brain kind of just shuts down? Well, today, we're going to tackle that exact feeling. We're going to demystify one of the most powerful skills in precalculus, simplifying rational functions. And trust me, by the end of this, you'll see it's way more straightforward than it looks. So let's dive right in with this quote because it absolutely nails it. It's just fraction reduction on steroids. Seriously, if you can simplify a regular old fraction, you've already got the key to mastering this whole thing.
I mean, think about it. You already know how to do this. You see 12 over 15, you find the common factor, which is 3, right? And you cancel it out to get 4/5. All we're doing today is the exact same thing, but instead of just numbers, we're using polynomials. It's the same game, just with slightly different players.
So here's our game plan. First, we'll go over the all-important rules of the game. Then we're going to solve a few problems, working our way from easy to expert. After that, we'll talk about the common traps to watch out for. And finally, we'll get into why any of this actually matters in the real world. Let's do it. Okay, before we just start crossing things out like crazy, we have to lay down the law. There are two rules that are totally non-negotiable. If you get these right, you are golden. And here is the single most important rule of all. You can only cancel factors. Things that are being multiplied. See on the left? That 3 is multiplying the whole x plus 2 group, so it's a factor. We can cancel it. But look at the right. That x isn't a factor, it's a term. It's connected by addition. It's kind of married to that plus 2. You can't just break them up and cancel the x. That's a huge no-no.
Now, this next one is subtle, but it's where so many people get tripped up. Think of it like this. A function has its own DNA, its own set of rules. When you simplify it, you might change how it looks, but you can't change its fundamental nature, and that includes its domain. So if the original function would break at x equals 2, the simplified version still has to respect that, even if the evidence, that x minus 2 factor, is long gone.
So what does that actually look like? What happens on the graph? Well, when you cancel a factor like that, it creates something really cool called a hole. The graph looks like a perfectly normal line, except for one single, tiny missing point. It's a fascinating little clue about the function's deeper behavior, and honestly, it's a little preview of some of the awesome stuff you're going to get into in calculus. All right, enough with the theory. Let's get our hands dirty and actually do some math. We're going to put these rules into practice with 3 examples, starting simple and leveling up as we go. Okay, example number 1. This is a classic warm-up problem. The key here is just looking for the greatest common factor, the GCF, in both the top and the bottom. Okay, so let's walk through it. First up, we factor that numerator. We can pull a 4x out of both terms, leaving us with 4x times the quantity x minus 2. And, would you look at that, we've now got a 4x on top and a 4x on the bottom. We can cancel those out. So our final answer is x minus 2 over 3. But, and this is important, we have to look back at the original denominator. It was 12x, which means x is not allowed to be 0. We have to carry that restriction over. Okay, time to level up a bit. For this one, we're going to have to factor both the numerator and the denominator. See if you can spot the classic pattern up top. The bottom is going to take a little more detective work to find those two magic numbers. So that numerator, x squared minus 9, that is a classic difference of squares. It factors out perfectly to x minus 3 times x plus 3. Now for the denominator, we need two numbers that multiply to 6 and add up to 5. That's got to be 2 and 3. So it becomes x plus 2, x plus 3. And there it is. Our common factor is x plus 3. We cancel those out, which leaves us with our final answer, x minus 3 over x plus 2. And, of course, we have to state our restrictions from the original denominator. X cannot be negative 3 or negative 2. All right, before our last and toughest example, I'm going to let you in on a little secret weapon. I call it the opposite trick. It's a super clever move based on a simple idea. Any number, let's call it a, divided by its opposite, negative a, is always negative 1. This trick is an absolute lifesaver when you get a problem that looks almost but not quite right.
So let's see this trick in action. On top, we have x minus 5. The denominator, 25 minus x squared, that's another difference of squares, right? It factors to 5 minus x and 5 plus x. Now look closely. We've got an x minus 5 on top and a 5 minus x on the bottom. They are so close to being a match, but they're opposites. This is the perfect time to use the trick.
And here's the move. We take that 5 minus x from the denominator and we strategically factor out a negative 1. When we do that, it flips the signs inside, turning it into -1 times x minus 5. And just like that, we have a perfect match on the top and bottom. We can cancel out the x minus 5 factors. That leaves us with our final answer, -1 over x plus 5. It's a really slick technique, right?
Okay, so now that you've seen the right way to do things, let's talk about the most common ways people mess this up. Avoiding these two traps is going to save you a ton of points on your next test, I promise.
Just to really hammer this home, mistake number 1, illegal cancellation. You cannot cancel the x squareds in that example because the one on top is a term. It's married to that plus 5. You have to factor first. And mistake number 2, forgetting the 1. When you have something like x plus 2 over x plus 2, they cancel out, but they don't disappear into nothing. Anything divided by itself is 1, not 0.
All right, so you've learned all the mechanics. But I know what you're probably thinking. When am I ever going to use this? Well, the answer might actually surprise you. This isn't just busy work. This skill is fundamental for a ton of real-world fields.
Yeah, seriously, where does this pop up? This is not just a textbook exercise. Simplifying rational functions is absolutely essential in physics, in engineering, in economics, even in creative fields like photography. Let's take a look at a really cool example.
This right here is the famous lens equation from optics. It's a core formula that connects the focal length of a camera lens, that's f, with the distance to the object you're shooting, d sub o, and the distance from the lens to the image sensor, d sub I. But just look at it. How would you actually use this to solve for anything?
To solve this thing for the focal length, f, you can't have those two separate fractions on the right. You've got to combine them into one. And how do you do that? By finding a common denominator and adding them, using the exact skills we've been practicing today to create a single rational expression. Once it's one clean fraction, you can just flip both sides to get f all by itself.
So I think the main takeaway here is that simplifying isn't just about making an equation look tidier. It's a really powerful tool for analysis. It lets us peel back the surface layer and find these hidden structures, like the holes in the graph we talked about. And that just leads to a much bigger, more interesting question. If simplifying can reveal that, what other hidden behaviors are just waiting to be discovered in the functions all around us?